Welcome to solverfy.
In this question, we have a particle in an infinite square well with this initial wave function. Psi x 0 is equal to a times psi 1x plus psi 2x. Okay, so for infinite square well, problem. Okay, so the diagram looks like this. A from 0 to a, and the potential is infinity. Okay, and then so the wave function psi 1x is 2 over a psi pi x over a, and then psi 2x is root 2 over a sine 2 pi x over a. Okay, we have E1 equals to pi square h bar square over 2m a square, and then we have E2 equals to 4 pi square h bar square divided by 2m a square. Okay, so first, there are 5 parts in the question. Okay, so in part A, we want to find A, the normalization constant. Okay, so we'll use the normalization condition. Okay, which states that the integral from negative infinity to infinity mod big psi x 0 square dx is equal to 1. Okay, so what you are going to have is mod a square, okay, psi 1 plus psi 2 star times psi 1 plus psi 2, okay, and dx, and then this is equal to 1, and then you are going to have mod psi 1 square plus mod psi 2 square plus psi 1 star psi 2 plus psi 2 star psi 1, okay, and dx equals to 1. Okay, since all the functions are real, so and then we have our all the energy eigenfunctions are normalized, so this is equals to 1, and we have mod psi 2 square dx is also equals to 1, and then psi 1 and psi 2 are orthogonal to each other, so we have psi 1 psi 2 dx is equal to 0. Okay, and similarly and psi 2 psi 1. Okay, so the above the line above will get 2 times mod a square is equal to 1, which means that mod a is equal to 1 over root 2. Okay, so this is our normalization constant for part A. Okay, in part B, we want to find the wave function in time and also the probability density at time t. Okay, so we are given this as the initial wave function. Okay, and we want to find the wave function at time t. Okay, what we need to do is just to attach the phase factor e to the negative I e1t over h bar, and then to each term. Okay, for psi 2 will just be negative I e2t over h bar. Okay, and then we define omega as e1 over h bar. so which is pi square h bar over 2ma square. So we can simplify the psi xt to become psi 1x e to the minus I omega t plus, and then e2 is 4 times of e1, so the omega will be 4 times minus I for omega t. Okay, so this is the wave function at time t. Okay, then if you want to find the probability density, okay, which is mod square, okay, so yeah, so just remember that psi 1x is root 2 over a sine pi x over a. Okay, psi 2x is root 2 over a sine 2 pi x over a. Okay, yeah, so I'm not putting the exact functions here yet, but if you want to substitute that, you can just substitute. Okay, so if you do the mod square, then you have half. Okay, so yeah, so just make it complete. Okay, so the mod square will be psi star psi, right? Okay, so the 1 over root 2 will become half. Okay, and then you have psi 1x. Yeah, because the spatial wave function is real, so I'm not going to put a star. Okay, but the time phase factor, from minus I becomes I. Okay, and then psi 2x e to the I for omega t. Okay, so this is the psi star, and then the psi without the star will be, you can just copy. Okay, and then you just multiply, so you have psi 1 square. Okay, so this term multiply with this term, the exponential term cancel out, and then you also have the psi 2 square as well. Okay, these two terms there's no time dependence, and then you have psi 1 psi 2 e to the minus I 3 omega t, and then you also have the psi 1 psi 2 e to the I 3 omega t. Okay, okay, then you continue the algebra. Okay, so here you can pull out the psi 1 and psi 2. You have e to the I 3 omega t plus e to the minus I 3 omega t. Okay, this can be rewritten as a 2 cosine, okay, using the Euler formula. Cosine 3 omega t. Okay, and if you want to substitute the functions inside here, so you have half times, so there's a 2 over a, okay, outside, and then sine square pi x over a plus sine square 2 pi x over a plus 2 sine pi x over a sine 2 pi x over a cosine 3 omega t. Okay, and then you can simplify further. Okay, so this is the wave function, the probability density, okay, of the wave function at time t. Okay. Okay, so that's for part B. Then we go to part C. Part C, we want to find the expectation value of position. Okay, so expectation value of position is, okay, according to the definition, psi star x psi um, dx. And since x doesn't operate, since x can be moved everywhere, so you actually get this x times mod psi x d star psi square mod square. Okay, so then you just need to copy what you have in the previous question, okay, to here. Okay, go from 0 to a, x times 1 over a, okay, sine square pi x over a plus sine square 2 pi x over a plus 2 sine pi x over a sine 2 pi x over a cosine 3 omega t and then dx. Okay, so here there are three integrals that we need to do. Okay, I'm just going to do them one by one. It makes it easier. Okay, so 0 to a x sine square pi x over a dx. Okay, this gives us a square over 2. Okay, this is also the same for x sine square 2 pi x over a dx. Okay, and then the third integral, which is 0 to a x, we have a 2 here, sine pi x over a sine 2 pi x over a cosine 3 omega t dx. And then if you use, so the cosine 3 omega t doesn't participate in the integration, it's a constant in this case. And then so if you use Wolfram, okay, and you would get we are going to get negative 8a square over 9 pi square, and then there's a 2 in front, and there's a cosine 3 omega t. Okay, so here, okay, you use Wolfram alpha. Okay, it will give you the answer. Okay, save you some time. Okay, and so then we just put everything together. Okay, so in the expectation value of x, you have 1 over a in front, and then we have a square over 2 plus a square over 2. Okay. No, I think this one is a square over 4. Yeah. Okay, and then plus or minus, okay, minus 16a square over 9 pi square cosine 3 omega t. Okay, and then you can cancel the a, so you have a over 2 minus 16a over 9 pi square cosine 3 omega t, and this is equal to a over 2 1 minus 32a over 9 pi square cosine 3 omega t. Okay, right, so this is the expectation value of the position. Then we need to determine the amplitude. Okay, the amplitude is 32a over 9 pi square of a. That should be, the a is not here, sorry. Yeah. Okay, after you factor out the a, so the a is not there. Okay, 32 over 9 pi square times a over 2. You can use your calculator, you get 0.360 times a over 2. Okay, and then the frequency, okay, the frequency is equal to 3 omega, okay, which is 3 pi square h bar divided by 2ma square. Okay, okay, next we want to find the expectation value of the momentum. Okay, expectation value of momentum, by definition it is size star, and then the momentum, the coordinate representation of momentum is h bar over I partial x. Okay, and this is a star, and then psi xt and dx. Okay, so this thing we need to do it carefully and step by step. Okay, so yeah, we need to do the differentiation first. So let's just write down what our psi xt is. So psi xt is 1 over root a sine pi x over a e to the minus I omega t plus sine 2 pi x over a e to the minus I for omega t partial x psi xt equal to 1 over root a pi over a cosine pi x over a e to the minus I omega t plus 2 pi over a cosine 2 pi x over a e to the minus I for omega t. Okay, and then here you can simplify by pulling out the pi over a. Okay, I'm going to ignore the h bar over I for the moment. Okay, later just put it back. Now, okay, we are just going to focus on multiplying the functions. Okay, so when we do this, before that, let's just write down the complex conjugate first. Okay, so this is the complex conjugate, and then we are going to multiply the psi star with the ddx of the psi. So we have pi over a square sine pi x over a cosine pi x over a. Okay, so we first write down the terms that the exponential terms cancel out. Okay, and then the mixed terms. Okay. Okay, and then we are going to integrate this thing. Okay. Then if you use Wolfram again, you realize that the sine and cosine with the same arguments, they just cancel out. They just give you 0. Okay, they don't cancel out, but they give you 0. Okay. Okay, because they are orthogonal. Okay. Yeah, so basically this is equal to 0 after integration. Okay, after integration. Okay, not in this when you multiply the two functions, but when you integrate. And then using Wolfram again, okay, so if you use Wolfram for the other two terms, to sine pi x over a cosine 2 pi x over a dx, and this gives you minus 4a over 3 pi. And then if you do the other one, 0 to a, sine 2 pi x over a cosine pi x over a dx, and this gives you 4a over 3 pi. Okay, so so when it comes to the integral, okay, the integral of sine xt dx sine pi star xt ddx sine xt dx, okay, you have okay pi over a square, and then you have negative 4a over 3 pi e to the minus I 3 omega t plus 4a over 3 pi e to the I 3 omega t. Okay. Okay, so the pi cancels, the a also cancels. Okay, so you have 4 over 3a e I 3 omega t minus e minus I 3 omega t. Okay, so 4 over 3a times 2i sine 3 omega t. Okay, and so the expectation value of p is equal to h bar over I integral of psi star xt ddx psi xt dx. Okay, so this is equal to h bar over I 4 over 3a 2i sine 3 omega t. Okay, so the I cancels and you get 8 h bar over 3a sine 3 omega t. Okay, so this is the expectation value of the momentum. Okay, so just want to highlight. Okay, you can do wolfram alpha here. Okay. Okay, in part 5 or in part E, we want to find the probability of getting each energy. Okay, so probability of E equals to E1 is half. Okay, and the probability of getting E equals to E2 is also half. Okay, it's basically because we wrote our psi x 0s in the form of ci psi I, right? And so the probability of getting E equals to EI is just mod CI square. Okay, and each CI in this case is 1 over root 2, so when you square it, you get half. Okay, then you need to find the expectation value of the Hamiltonian. Okay, the expectation value of the Hamiltonian is equal to the probability times the individual energy, and you sum them up, so it's half E1 plus half E2. Okay, so half E1 plus E2, and you know that E2 is for E1, so we have 5 over 2 E1. This is 5 over 2 pi square h bar square over 2ma square. Okay, yeah, so the expectation value of the Hamiltonian is in between E1 and E2. Okay, and so this is the expectation value of Hamiltonian, and then this is how it compares to E1 and E2. And that's all for this question.